Hi, I'm Prajit Sen, and today I'll be presenting an AI assignment. So our problem statement is solving the cryptarithmetic problem. So before we dive into the problem, let me introduce my group. So my group name is PAS, and I am Prajit Sen with my team members Alok Kumar Rathod, Siddharth Chaudhary, and Anaswara Krishnan. So now, what is a cryptarithmetic problem? The goal of this puzzle is to assign each letter a unique digit from 0 to 9 such that a given arithmetic equation holds true. Now, what is the challenge of this problem? Each letter represents a distinct digit and the numerical sum must be valid. So, throughout this presentation, we will be taking a classic example, that is send plus more equal to money. Now, what our task is to assign SENDMORY unique digits. The solution, assigning digits such that the sum is arithmetically correct. Now the solution for this problem is 9567 plus 1085 equal to 10652. Now let's see the constraints. Every problem statement has some constraints. So does the cryptarithmetic problem. Now to solve successfully a cryptarithmetic problem, there are several strict rules that must be followed. First rule is unique character digit mapping. Each character stands for a digit, and repeated occurrences of the same character denote the identical digit. Second is leading digit rule. Numbers found by the words in the equation cannot start with 0. For example, as I mentioned, send. Now the letter S shouldn't be assigned 0. Or take money for example, M cannot be assigned 0. Again, no duplicate digit assignment. No two distinct characters can be assigned the same digit. Each, each letter should map a single digit. Now, before solving the statement, let's get brief about the state space. Now, understanding this search space is very critical for analyzing algorithm performance. So, let us first define what is our state. A state represents the current partial assignment of digits to letters. Example, M is 1, S is 9, E is 5. Now the maximum search space for n distinct letters is 10 pm. Now let's see what is our initial state. Now the search begins with an empty assignment. That means no letter has been assigned a digit. This is our initial state, and the successor function, that is new states, are generated by picking an unassigned letter and assigning an unused digit. Pruning occurs if constraints are violated. Example, from M1, assigning S equal to 9 leads to M1 and S9. What is our goal list? A state is a goal if all the letters are assigned, leading digits are not 0, and the mathematical equation is satisfied. Goal state is full assignment where all letters have digits and the arithmetic equation is satisfied. Algorithms under the microscope. Now, what we will do is we will be analyzing the performance of two prominent search algorithms that we'll be using. The first is the before we analyze, let us understand how does it work. How does the algorithms work here? Now, breadth first search. That is a very famous, common search algorithm, BFS. What it does is basically it explores all the nodes at the present depth level before moving on to the nodes at the next depth level. Explores level by level. It guarantees a shortest path to the solution and can be memory intensive. Next comes is best first search, BEFS. Now what it does, it expands the most promising node chosen according to a specified rule, often a heuristic function. Uses a heuristic to prioritize promising nodes, potentially faster by focusing search, but the thing is it may not guarantee shortest path. Now let's see the BFS approach. What is the working principle? As I've already mentioned, it explores search space level by level. So at depth D, it will assign all the possible assignments of D letters before moving to depth D plus 1. Now let's see the performance characteristics. First, we'll take completeness. Always complete. You'll always find a solution if it exists, as the state space is finite. Optimality, not applicable for constraint satisfaction problems like cryptarithmetic, not about path loss. Now let's see the complexity analysis. We'll first start with the time complexity. Branching factor equal to 10 choices per letter. So we note that uh, if suppose there are n digits, so n letters, so there are 10 choices per each letter at the initial state. Now for n letters, the time complexity, the depth will be n will be the depth. So the worst case will be 10 to the power n, which is obviously impractical. Now, if we see the space complexity, what it does, it basically stores all the frontier nodes. Memory explores the space complexity is O of B to the power D. That is, B is the branching factor and D is the depth. So, if we see the empirical behavior, BFS is too slow and memory heavy for cryptarithmetic problems, making it impractical beyond very small puzzles. This was such approach. Now, as I've already explained, the working principle expands nodes based on heuristic function. For example, heuristic how close the partial assignment is satisfying the equation send plus more equal to 1. Now, let's see the performance characteristics. Let's see the completeness. It is complete if the search queue is fully expanded. Optimality, it's not guaranteed. The first solution found may necessarily not be the most efficient in terms of search steps. Complexity analysis. Now, if we analyze the time complexity, it is still exponential in the worst case, but fewer states expanded if the heuristic is highly informative. So, in some terms, it's better than the BFS, that is the breadth first search. Now, if you look at the space complexity, it needs to store the frontier. Still large, but significantly less than BFS if the heuristic prunes the search space effectively. If we see the empirical behavior, it performs much better than the BFS. An effective heuristic minimizing some error leads to exploring significantly fewer nodes, making it more practical. So let's put the theory to test. Let's put an experimental setup. As I've already mentioned, we will take an example that is a very common example. Send plus more equal to money. Our task will be to assign each letter a distinct digit. So now we'll be comparing on the basis of three factors. One is the metrics will be recorded as time to find the first solution, number of nodes that has been expanded during the search, and the last that is the maximum memory consumption. Now to test this, we have implemented algorithms in C++ so that there's a fair comparison. So let's see what was our results when we tried to compare in the code how best first search performed way better than BFS. So if you can see here, performance comparison wise, breadth first search too long to measure. The nodes expanded were massive, max frontier size exceeded the memory, and time taken was around infinite. If you see the best first search, it was around 0.005 seconds. 200 nodes has been expanded. Max frontier size was around 50, and time taken was comparatively way faster than the breadth first search. So it best first search significantly outperforms BFS in both speed and memory efficiency for this problem. Now, if you see the results, as you can see, the nodes expanded for BFS is way larger than the best first search. Sorry, yeah, it's quite large compared to best first search, around 10 times the BFS has nodes expanded. If you see the max frontier size, there's a huge drop in the max frontier size when you see for the best first search compared to BFS. And you can also see for the time taken, it's around 14 seconds for BFS, but for best first search, it took only around 1 second. BFS struggle to complete the task within practical time and memory limits, highlighting the inefficiency for problems with large search space. It is good for handling a small search space, but for large search space, it's preferred. Best first search is much more preferred than BFS. Best first search, guided by an effective heuristic, found a solution rapidly with minimal resources usage. Okay, so we come to our conclusion. So our conclusion is that our analysis highlights the fundamental differences in the algorithm approach to the cryptarithmetic problem. So we have taken two algorithms and we have compared the performance of the two algorithms, that is BFS and the best first search. So the problem complexity. Cryptarithmetic problems are inherently combinatorially complex, requiring efficient search strategies. If you see the BFS limitations, while BFS guarantees completeness, its resource heavy nature makes it impractical for larger instances due to exponential memory and time demands. If you see for the best first search efficiency, best first search effectively leverages heuristics for efficient solving, significantly reducing the search space and resource consumption. Heuristic importance. The choice and the quality of the heuristic are critical for the success and performance for best first search. If you see the future directions, future work could explore hybrid approaches, combining the strengths of different algorithms and further optimizing heuristic functions. Thank you.